really the only way you can know for sure you drew it correctly, because the formal charges have to add up to the total charge, whether it's -2, -1, or 0, and there's always different ways to do these structures. So, for example, you could do this structure with all single bonds, but it's not going to be as stable as this one. All right, and this is it. I only got about 7 minutes here or whatever. I'm going to go through these, explain again how to do formal charge, why one structure is stable and one isn't. I'm going to explain this term called resonance. These three structures have resonance. Okay? So O3 doesn't look like that, and there's other reasons why, but because it exhibits resonance and the bond length changes. So I'm going to get to that in a second. All right. So let's do the formal charge on this one. And now, first of all, if we were to do this, so let's say 1, 2, 3. So here's our. So there's our dot structure before we start making double bonds. We have those -2 dots waiting. So if I take one dot, put it here, one dot, put it here, so those are now involved. And if I take, I don't know, let's say this dot and put it here, or I took that dot and put it here. Either way, it doesn't work for this one. 2, 4, 6. This has 8, this has 8, and this has 8. That is really bizarre. Carbon really does not do that. Okay, you're going to hopefully pick up things along the way, and you just start to realize that that's not normal. That doesn't happen. So carbon doesn't keep a pair of electrons. That doesn't work. So even if we took those and put them here, now it only has 6. So all single bonds doesn't work. Again, I'm just making sure you understand the process here, right? So I have all my dots, I have my single bonds, they're all paired up, but not everybody has a full octet. And if you do the formal charge, this ends up being 6 minus 7. 1, 2, 3, 4, 5, 6, 7. So that's -1. 6 minus 7, -1. 6 minus 7, -1. This is 4 minus 3. 4 valence, 1, 2, 3, so +1. So does that up to -2? Yes, it does, but it doesn't follow all our rules. So everything has to work out, right? All the rules and formal charges for it to make sense and for it to be correct. So this is wrong, not because the formal charges are wrong, but because this doesn't have a full valence shell. Okay, complete octet around the C. All right, so again, I'm doing it slow and kind of saying this is the thought process, this is how I want you to do it. So now you get to this one, and now 2, 4, 6, 8 around here, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everybody has 8. That's good, that's stable. All right, all the electrons are paired up. This formal charge is 6 minus 7, -1, 6 minus 7, -1, 1, 2, 3, 4, 5, 6 minus 6 is 0, 1, 2, 3, 4. So this is a great example of more zeros, more stable, and everybody has an octet. So that's why this one is correct. Now, Tristan could have drawn the double bond on any of these, because remember, these things actually exist in real life. So if I rotate this or I move it around and I draw it a little different, it doesn't really matter, right? If this double bond is here instead of here, it's the same exact structure. And if this double bond is here instead of there, it doesn't matter. It's the same exact structure. I want you to write this down. That's called resonance. In chemistry, resonance is when you have what's called, and I need you to write this word for word, delocalized electrons. Delocalized electrons. And delocalized electrons are only found in double and triple bonds. They're called pi bonds. We're going to get into that. Delocalized electrons can move between atoms. That's kind of the basic explanation of it. But really what it means is when these ions or molecules form bonds between each other, the double or triple bond can move around. That's like the layman's terms there. The bonds can move, but the real explanation is the electrons in this bond, let's say, are able to move around freely within the molecule, and that's called delocalized. When we get into hybridization and bonding, and we're drawing orbitals overlapping, it gets kind of crazy. I think it's cool, personally. It makes more sense. So we'll get there. But right now, you just need to know this structure has resonance because that double bond can move. This double bond can move, it has resonance. This double bond can move. There's only one double bond over here, and that can flip-flop. And how do we know that? How do scientists know this has only one double bond, or that only has one? And how do they know it can resonate, or it has resonance? Here's how. When you measure the bond length of these, which is not easy, but it can be done, when you measure the bond length, it changes. So this one, and this one are always changing somewhere between a single bond and a double bond. So it's kind of like the bond length, there's like an average between the three, and that's how they know the double bond can change randomly. Because it'll be shorter, then it'll be longer. It'll be shorter, then it'll be longer, and that's because it's kind of fluctuating. So that's, again, called resonance. So it's kind of interesting and kind of cool how that works. All right. So a couple things here we're learning: dot structures, formal charges, how to do that. Now applying resonance. Resonance only works if you have double or triple bonds and there's more than one bond. In other words, if you take the cyanide ion, yeah. So again, that's weird, but it does happen sometimes. But if you take this, how come this doesn't have resonance? It can't go anywhere else. It is what it is. There's only two atoms involved. So you need more than two atoms, right? You need a central atom and then at least two outer, right? At least two. That's the only way that can work. So this one over here actually looks like that. That's what that one looks like. All right. This is correct. This is correct for the exact same reason this is correct. You can't have all single bonds here because even though, yes, 2, 4, 6, 8, everybody has 8, look at the formal charges. -1, -1, -1, 1, 2, 3, 4, 5, 5 minus 5 is 0. What does that add up to? -3. We need it to add up to -1. So that doesn't work. So you got to make a double bond. 1, 2, 3, 4. This is +1, -1, -1, oops, that's 0. 0. So this -1, -2 cancels out here, so you have a -1. So that's the point of the homework there. There's the numbers over there. I'll text it later. Is to understand this is wrong, here's why. This is right, here's why. Okay? Now over here. Hopefully I have time to explain this for the bell. If we go back to the structure, dang it. Alright. We'll talk about that on Tuesday. You got 4 problems, but I think there's multiple parts to some of those, so have fun with that. What else do we have going on? Problem set. Is that Tuesday too?
No, you made it Wednesday.
14th is Wednesday? Oh, that's better. Okay. Alright, problem set Wednesday. Those book problems due Tuesday. If you need anything from me today, just come see me.